Alright. Hi, I am Alex,
And I'm Bailey.
and our presentation is on pi. Now, does anyone know what pi is? Anybody at all? Is there participation right here? Expect an answer. Yes, Mr. Kruger in the front row.
The circumference of a circle, the ratio of the circumference of the circle to its diameter.
You're really close. What pi really is a delicious dessert created by combining ingredients such as cherries, apples, sugar, flour, butter, and cinnamon in a delicate flaky crust. But for answering, you can have some pie.
Oh, awesome. Right now?
Yes. Caramel apple, or
So I actually have to ask,
Sugar
should
and
we get by?
Well, this is.
and if the rest of you would like to join me in getting pie, you may go ahead right now. Hey, why are you following you?
These look like they're real fools.
I don't know how to eat a strawberry with a spoon. It's just gonna make a mess.
Sorry, I didn't
I
have
can't eat cleanly with proper utensils.
Okay, but in all seriousness, Mr. Kruger was right, and pi is a number, approximately 3.1415926, which was established to represent the ratio between the diameter of a circle and its circumference.
And why is pi important? Well, pi has been used repeatedly in our school, and we wanted to dive a bit deeper into the actual use and foundation of the number and how it applies to advanced subjects. And pi, come on, guys. So, pi is very old, very, very old. Farthest that we could find was the ancient Babylonians finding it around the year 1900 BC, where they approximated pi at 3.125 by multiplying the radius of the circle times 3, and then they technically got the value of pi. Now, pi had been approximated by other civilizations such as the Egyptians, even the Chinese, but in the Western world, the Greeks are known to the ones who have first discovered it. Archimedes is the one that really used the Pythagorean theorem to find the area of two regular polygons, approximating the value of pi between 3 and 1/7 and 3 and 10/71, which is close to the approximation we use today.
And how it applies to mathematics is kind of obvious. It's a math term, and so pi is used in many different areas of math, but the primary ones are geometry, clearly in terms of circles and spheres, and also trigonometry, and then aspects of calculus that involve the prior two subjects on a more complicated basis. Now here's kind of where pi gets interesting, because as proven time and time again, pi is irrational, which makes it impossible to express pi as a fraction of two whole numbers. And this irrationality makes the application of pi a bit difficult, because it is impossible to express the circumference or area of a circle without using pi. However, pi was created specifically for this purpose. So what we have here is kind of a loop in reasoning where we say we created this and we have to use it to express these values. And so if pi is truly rational and goes on forever without repeating or terminating, and every circle contains a ratio of pi, how then can a circle have a definite circumference? So as you go on into each decimal place of pi, it increases. So if you have 3, 3.1, and it continues so forth there forever, theoretically. And because the circumference of a circle is directly influenced by the value of pi, this would mean that the circumference also increases every time another decimal of pi is added. If this were true, it would mean that circles are increasing forever in size, because the factor of their size is forever increasing. This means that every circular object which exists in our world would be in constant motion and always increasing. So you can use the summation series to approximate pi, and it will become more and more accurate for every additional term you go as you approach infinity. And since the circumference is diameter times pi, it is also true that the sum of each additional term can be used to approximate the circumference of a circle with more and more accuracy. Next, we did some approximations using a summation series. So if you start at term 0, you get 6.928203203, and then at 1 it drops down to 6.158402871. So this is an alternating series going back and forth because you're adding and subtracting numbers. And as you can see, it quickly goes to about 6.283181022, and it would go on forever from there, increasing and decreasing, and eventually adding more and more decimal places until forever. And so, essentially what we're saying is that any circle that you have is always increasing in circumference, because pi never ends. So, let's look at it on a little bit bigger scale.
So, the universe. There are many theories as to the shape of the universe, and one such theory is that the universe is a sphere. Now, this really fits into our topic of pi because the equation to find the volume of a sphere is 4/3 pi r cubed. So, with pi and it ever expanding, it is safe to say that the volume of the universe is forever expanding, which it is. And yeah. So, we have one relationship between the radius and pi, which is the universal volume, and then the scientific thought that thought to be ever increasing, and the one ratio, which is the circumference of a circle, that is thought to be fixed because it is, 2 pi or something like that. And this poses a little bit of a discrepancy because if two circles are the same thing, one is fixed and one is not, are they not the same thing? Would not both be fixed or both be ever increasing? So this is where we got into some big numbers, and I feel really bad about this, but, so, the universe is roughly 13.8 billion years old, and is, as far as we can tell, 46 billion light years large. Now, light years is the distance that light travels in a year. 46 billion of those is a very, very large number. So, overall, let's see, I'll do this, converted light year, what is this? Light years to meters, and then took how many seconds there were in a year, and multiplied to find how far light traveled in a year, and then multiplied by the 46 billion light years, so the technical diameter, and divided by 2 to find the radius, which is very, very large, and I prefer not to try and say how I prefer not to try and say it. And so, with this scenario, trying to stick with the sphere model, we're assuming that the critical density of the universe is greater than 1. And so this would apply the volume, which we forgot to change that on our presentation. Volume does not equal 4/3. It equals 4/3 pi r cubed. So, plugging our radius into our volume equation, we are going to get, let me see if I remember this, 1.370894,943 times 10 to the 63rd. And that's very large. So that's the volume of the universe, in a sense. So looking at the equation for volume, we can find the rate at which the universe is expanding by taking the derivative of it, which would be 4 pi r squared dr dt, which dr dt is the rate at which the radius is changing. Now, we use the radius of a golf ball because in the time from the singularity exploding to the point where it kind of slowed down to a constant rate, the universe, in the first 10 to the negative 34th second, inflated from the size of a subatomic particle to the size of a golf ball, which means it would be doubling its size about 90 times in that small amount of time. So that would not have been fun to try and measure. So we decided to stick with the golf ball where it kind of went to a relatively constant rate of growth. And then we have the radius of the universe once again. And so we can take those, we can subtract the radius of the universe from the radius of the golf ball and divide it by the amount of time the universe has been growing, minus that 10 to the negative 34th second. And we get about 1,553,199,029,000,000 meters per year. So that would be the rate at which the radius is changing. So we can plug that in to the derivative of volume to find the rate at which the volume is changing, which would be this number times pi, because pi is still part of the equation.
The universe is thought to be increasing at a slower rate. And if your radius is increasing at a constant rate, that doesn't quite fit that theory. And so, if you take an application of pi and the fact that its ever-expansiveness is increasing at a smaller rate, clearly as each decimal place is less than the prior, that would explain the change in rate of the expansion of the universe. Then we took another step and went to Cancer. And it's been discovered that the detonation of nuclear bombs causes a sharp increase in cancer rates in the area of detonation. And this is primarily because the radiation which comes out of the bomb causes cancer.
So this is a picture of a theoretical blast radius for a nuclear bomb, and it shows how the pressure from the blast decreases as you get further out from the actual spot of detonation, which would explain why radiation is worse towards the actual center of the blast and less severe as you go further out. So we started with the smallest technical nuclear bomb we could find, and that would be the Davy Crockett. The US produced it. I know, interesting names for these things. And the radius of its radiation is 1,400 feet. And if we put that into the equation for circumference, the circumference of the Davy Crockett's radiation would be 2,800 pi feet. And then the area of the radiation would be placed, of course, we would put the radius into the area function, which is pi radius squared, and would result in a area of 1,960,000 feet squared. So the estimated fatalities of this detonation alone would be 120 people, and the number of estimated injuries amounts to about 420. Now, we get these numbers by dropping it on St. Cloud.
So that's dropped right down by the Paramount Theater there. And so you can see it goes almost up to Perkins on that side and past Lake George on the south. So for the smallest
I
nuclear
just
bomb,
care, where does it go when it heads northwest?
just past the corner of 2nd Street and 12th Avenue.
Where's Whitney in this picture?
You're safe.
Farther north, I do.
Yeah, you're good for now.
So that was the smallest nuclear bomb that's been tested.
And now,
Next, we took a little bit bigger step and went with the Castle Bravo. And this is the largest bomb that the U.S. has detonated. The radius of its radiation is 2.25 miles, and the circumference of a circle would then be 5.5 pi miles. The area would be 5.0625 pi miles squared. And the estimated fatalities from this bomb would be 115,690, and the injuries would be 28,580. So if we were to place this bomb theoretically in the same place we placed the last bomb, it would look more like this. Down here we have,
Royalton up there?
that's Annandale right there. This is Foley, so you're heading up towards Princeton.
Oh, that's, okay, it goes past Collegeville. Yeah, a lot past Collegeville.
It's larger.
Yeah, just a bit.
So we went back to the beginning.
Yeah. The beginning, we mean the first atomic bomb that was technically dropped at the Trinity test site with the Manhattan Project, codenamed Gadget. So the radius of its radiation is 0.87 miles. So the circumference of the blast would be 1.74 pi miles, and the area would be 0.7569 pi miles squared. The fatalities, if this were to be dropped again on St. Cloud, would be 13,280 people, and the injuries would be 16,890 people.
Here's a little visual for that one. I don't think Whitney's safe on this one. Northway's up there, so you might be good still.
No, we'd be okay.
Yeah. So that was the first one. That was the very first instance. And going back to our idea of pi, because pi is infinitely growing, and the radius of radiation would be infinitely growing with pi, if the first atomic bomb gadget was set off July 16, 1945, then we would expect the radiation from that singularity, as with the universe, to expand endlessly and affect the entire Earth. But since that didn't happen, it's not really practical.
Wait, didn't? Wait,
Oh, wait.
wait.
Look at that. Oh, look at that. It did happen. Cancer rates started to spike around 1955, so about 10 years after Gadget was dropped. And if you look at that, let's say 1955, 1945.
About 10 years?
About 10 years, yeah.
I'm in calculus, I don't do basic subtraction.
And so with that, some people say that's a bit of a time frame for cancer to start. And we thought that also until we looked a little further into it, and research by the Radiation Effects Research Foundation, which is a cooperative research team between Japan and the US, two very accredited scientific countries. They state that the effects of nuclear bomb radiation begin to present themselves about 10 years after exposure. So again, 1955 minus 10.
That's 10. Interesting. So, to wrap things up, Pi is an ever-increasing irrational number, and this expansiveness forces circles, true circles, to expand forever. And since they are expanding forever, it is no longer acceptable to call everyday objects, everyday round objects, circles, because the only objects which are true to the pi ratio are circles, and the rest are simply round-ish.